Hey guys, so in a previous video, I discussed a DFS based or level order traversal based, sorry, as well as a recursive solution for this problem of basically adding these right next pointers. In this video, I'll discuss an iterative solution for it. So just to reiterate the problem is that we are given a perfect binary tree and we have to populate all these uh, extra nodes which are called the next nodes, which points to the immediately next node, next guy on the same level. So I'll make use of the fact that it is a perfect binary tree, right? And so to walk through this tree iteratively, let me just show here. I'll again do a level order traversal, but I'll do the level order traversal iteratively. And the way that I'll do that is I'll walk from one level to another through these left pointers, the left pointers on the boundary, right? So first level will start with one. Second level, to go to the second level, I'll go to one's left. To go to third level, I'll go to two's left. This is how I traverse down a level. And the way I'll traverse across a level, I won't use a parent left and parent right. To walk across a level, I'll rely on these next pointers that we're adding, right? So when I'm traversing across this level, I'll just choose two's next, and then three's next is null, so that level is complete. And after that, I'll go to two's right. Sorry, two's left, right? And then similarly, when I'm traversing this level, I start with this level, I can go from 2's left 4, and then 4's next 5, 5's next 6, 6's next 8, 8's next is nothing. Then I'll move on to the next level, which will be 4's left. So I have to keep track of 2 pointers. One obviously I have to keep track of is this level start pointer and a current pointer. And when I'm at a specific level, when I'm at a specific node, I'll connect its left and right. So in this case, 2, I'll connect left and right. And if 2 has a next, which in this case, then it's going to connect 2's rights to 2's next left. So let's try and code it up. So we'll call one node as a level start node, and let's initialize it to root, and another node as current node. Let's initialize that to root as well. And well, the level start node is not null. Now we have to handle current. So within each level, we'll traverse again, and we'll do while current is not equal to null. And we'll start definitely current as well as the level start node itself. What do? We set up current of left is not null, then current dot left dot next equals to current dot right, and if current dot next is not null, then current dot and current dot right is not null as well. Then current dot right dot next equals to current dot next dot left. And then you go current equals to current dot next, right? This is what is helping traverse the level. Once the level is done, you move to next level, which is level start node equals to level start node dot left. And at the end, we want to return root. So yeah, that root remains the same. We never touched root. Yeah, so this is the algorithm. Let's quickly do a walkthrough here. We start with the level start node as root, and while root level start node is not null, that means number of levels. So the first level, current equals not equals to null. We set its left and right. Current's left is not null, so we connect 2 and 3. Current's next is null, so we don't execute this line. And current equals to current dot next. That means current becomes null. Then we come out of this while loop, and we do this where now the level start node is 2. Current is set to 2. Um, so we connect 4 and 5. 2's next is not null, so we connect 5 and 6 through this. And then we move to current dot next, and we move to 3, which will help us to connect 6 and 7. 3's next is null, so I cannot connect 7 with anything else. And current moves to current dot next, which is null. So we move out of this, and we go to level start node is equal to level start node dot left. So we go to 4, and we do the same thing. Uh, when we come down here, we walk through each of them. Now maybe we could prevent this last loop by walking through each of them, and we see if current dot left is not equal to null, we could avoid walking through each of these nodes. If there is one guy whose left is not null, then we know we can break. So for the last node, so maybe instead of this, we do, well, because there's nothing to do for these. So while level start node is not equal to null, and level start node dot left is not equal to null, right? If it's not the leaf node, and because it's a perfect binary, just checking one child is sufficient. And then we know that these are all leaf nodes, so we don't need to do anything for them. In which case, because I have checked this, I don't explicitly need to check for these conditions anymore. So I can maybe do this. Don't need to check it's right as well. It has to exist. It's not the leaf node. So we do this. Yeah, so this is fine. And what if the root was null? If root was null, then we would never go inside and we'll return root as null, which is working as well. This looks good. Let's do a run code. Okay, semicolon. Right, this works. Let's do run example test cases and submit. All right, so this works as well. All right, so that's it for this.